Good morning, good afternoon, or good evening. This is the first video in the Step 3 2024 series, and in this first video we'll discuss a bit about what this series is aiming to do, and then start to have a look at things like exam technique, exam timings, and the unique part of the STEP papers, question selection. So the aim of this series is to provide you with a full set of videos for all the questions within this Step 3 paper with a blind look. So what do I mean by blind look? I haven't studied these questions before. I'm not going to study them before tackling them in the video itself. So it should be a view of how someone would tackle this style of question in an exam style situation. I'll hope to explain a lot of my thought processes, particularly around exam technique and error spotting. It's very difficult often to know whether you've gone right or wrong. So having really strong techniques to discover that you've made an error and then going to find where that error is incredibly powerful. STEP itself is a very unique style of paper in that there are 12 questions on the paper, but you're only expected, or you're only actually marked on 6. So any more than 6 that you do will not gain you any extra credit. And if you do end up doing 7 or 8 or tackling 7 or 8 questions, then something about your question selection and your exam technique in that direction has gone off. You will get a very strong grade. It's graded S1, 2, 3. You'll get a strong grade, a grade 1, if you do about 4 questions well. So our aim really should be trying to do 4 questions really well, and then any other time that we have, trying to tackle the odd extra one. Therefore, in the 3 hours that you're given, you should be spending roughly, if you're doing 4 questions, that's 45 minutes. 6 questions is 30 minutes. So you're spending between 30 and 45 minutes per question. And if you look down some of the videos in this playlist, you'll notice that most of them are in that more 35 to 50 region, because of course explaining your reasoning as you go does take a little bit longer. But we're aiming for about 30 to 45 minute question for each one. Now, another strange thing about STEP is you won't be able to do some of the questions. Some of the questions will be too difficult, or using a skill set that you haven't perfected, or you're just not naturally as competent with. So question selection is super important. You are only picking 4 to 6 questions out of 12, so you want to pick the 4 to 6 which match your strengths as closely as possible. And as you practice these papers, you should be starting to spot the patterns of which styles of questions fits best for you. I know for me personally, I much preferred the algebraic. I preferred things with an unknown concept, something which the question introduces to you in the question itself, and then asks you to use it, and the stats questions. I found that the ones I struggled more with, because I'd either make more errors, or they take me longer, or I didn't spot the intuition in the time that I gave myself. I struggled with things like the geometry style questions. That's both vector, shape, and coordinate geometry questions I struggled a lot more with. And the mechanics questions. Although in A-level itself, I really enjoyed the mechanics module. I was very successful in the mechanics modules. When it came to these questions, those often were a little bit more challenging. I couldn't complete them as quickly, and I often made more severe question breaking errors, which meant I couldn't complete a lot of those questions as comfortably. So knowing what your favourite topics are is incredibly important. We're now going to read through this paper, look through each of the questions. I like to put a little code next to each question, either a a tick, a question mark, or a cross, depending on whether I would tackle this as one of my 4 to 6 questions. And of course that changes as the exam goes on. I'm hoping that I can find 4 questions which I tick, maybe 3 or 4 questions which I'm not sure about, which I'll come back to after I've done my 4 strong questions, and then the remaining, what would be remaining then, 4 to 5 to make the 12 that I just wouldn't touch in the exam situation. So we're going to read through each of these. We're going to see if the question itself has any tricks which I can spot straight away. If I can spot the trick straight away, then I'm likely to put it as a tick. If there's a topic which I don't like and I can't spot the tricks, it'll go as a cross. And then maybe if I'm semi-certain about most of it, but can't really spot it all straight away, then it'll be a question mark to come back to later. So let's read through the paper, and at least for my skill set, let's pick which questions we would focus on. Now, question one is almost always easier than the rest of the paper, so they're trying to lead you in quite nicely. So even if this isn't a topic which you're particularly strong with, often worth trying this as one of your 4 questions, because it's just built to be slightly easier. So question 1 is talking about the sum of this series. It's given you a general fact about the infinite sum. Straight away when I see this, I'm thinking method of differences. So it's set up some kind of identity. We're then doing the sum, which does indeed look like it's something, and then the method of differences part gives us that. Showing further, well then this looks like a direct result from this statement, so I'm happy with that. Part 2 is then trying to find a different sum. Well, I'm expecting that's going to do a similar thing to part I, maybe partial fraction it and method of differences, hence calculate, and then show that. This looks like a very comfortable question. There's nothing in that which surprised me. I'm going to have to spend some time doing the question, but I think I can get through that one quite comfortably. That's a definite have a go at. Question 2. We've got some inequalities. Well, this is they're both quadratic inequality and their modulus. If I square them, then the modulusness can disappear. Need to be a bit worried about whether I destroy or create extra solutions, or I could even think about the graphs. So those seem quite comfortable. Part 2 looks similar. We've got a function, and it actually asks us in particular to consider a particular thing to show that it goes to 0 as x goes to infinity. That seems fairly reasonable. Let's just expand out. There's some dots going on there. And then a sketch to look for. So basically looking for points of intersection between these two, which is exactly when f of x equals 0. Find the value of m and the corresponding value of c, so the solution set is that. So that's kind of undoing part I. So that seems reasonable. And then getting even more extreme, we've now lost all of the coefficients in the question. And it's even backwards as well. Now the quadratic is modulus. Maybe that's a graph attack. We can draw a quadratic, the modulus of a quadratic as so, and then we've got a straight line. We've got a double set of inequalities, so we need that straight line to cross in multiple ways. Again, most of that question I can see at least a way to attack it comfortably. Again, gonna need to spend some time working through the details, but that looks like a strong question. Question 3. This is now Lun. So we've got a function. Show that that has a positive gradient. I can differentiate and do that quite comfortably. Find the values which has a negative gradient. For again values of c, I can do that quite nice. It's given that for all positive, so it's giving a limiting value for g, and we're trying to sketch them in certain cases. Well, that looks like a follow-up from part A and B. Once I know when it's got positive gradients, I can then sketch the curve quite nice. And again, it's worth knowing that the boundaries of these are giving us stationary points. So we also know where stationary points of these curves are, which is also incredibly useful for such a sketch. F is now defined as so. I'm now comparing F with G. Maybe E to the G is something. There's certainly a link there, but it's going to be now very similar skills. Is decreasing, has a turning point, etc. This looks relatively comfortable. This again is just algebraic differentiation calculus kind of stuff. Won't be easy, but I feel like doable. And this is the first question which actually scares me. One, for the fact there's a lot less writing. That always seems to be more difficult. But it's talking about angles. It's talking about the geometry in coordinates. Show the acute angle between two lines is 45 degrees. Then we have that kind of statement. That this you should recognize as a tan theta minus theta 1 minus theta 2 style thing. It's a tan addition law. So that seems quite reasonable to tackle. This you should recognize as a parabola. So is that kind of shape. If P does not equal Q, show that the tangents to the curve with x coordinates P and Q meet with x coordinate there. So we need to find some tangents in general, put in the point of intersection. That seems reasonable. Show further that any tangents to the curve which are 45 degrees meet on that special curve. Okay, that's likely to be applying part I in some way. And then show that the acute angle between any two tangents which meet is constant and find that angle. So that feels like an adaptation to both part I and part I. I'm going to put this as a question mark only because I know this topic I often struggle more with, even though I think I can get most of the way through this. It won't be my second or third question, it might be my fourth or fifth question. Question 5. Of course, step 3 is now based on further maths, so we have M and N being matrices. We define the trace, prove that the trace is symmetric, and get an expression for the sum. That's very reasonable. This is the kind of question which I'd call an unseen concept, which the more questions you do, the more advantage you get, because you see more of these concepts. I've got an advantage here that I've dealt with matrices at a much higher level, so trace is something I'm already quite familiar with. If we carry on, we can now differentiate a matrix. Not something I've done before, at least not in recent memory. So we differentiate the matrix, show that something about differentiating the determinant. Well, that looks quite unpleasant. That looks really unpleasant. I'm going to really struggle to think about how to tackle that. Now, we are in the 2x2 world, so actually we can just do this algebraically on a general 2x2, and it might just work. And then part 3. Part 3, we're now solving a matrix differential equation. That's terrifying. Show that certain things are independent of t. Okay, well, we're likely to apply part 2. In the case where n is that and m is that, when t is 0, find m as a function. Okay, so this is now solve the differential equation, basically. You've got n as a general thing. Well, this feels like it's just 4 differential equations, one in each component, once I know what t is, because I can work out mn and nm. And then finally, we've got an even simpler, inverted commas, differential equation. The trace of M is non-zero and independent. Is it true that? Yeah, I'm going to have to apply a lot more thought to that, try to think about what's going on with the rest of the question. Nothing obvious is jumping out at me straight away. This is a question mark. It's on the higher end of question mark because I know these introduce a new concept questions I'm quite good at. So again, will likely be my question 5 or 6 of the paper. Question 6. We got a coupled differential equation, satisfies by those. Told us to do a special combination by subtracting them. And initial conditions, okay, that seems simple. Given that, find a constant that ensures a particle is at the origin at some later time. That seems sensible. We've now got triple simultaneous equations. Show the particle as, if the particle is at the origin, it is necessary that the y naught is some condition. Well, that I'm sure I'm going to apply some version of I part A. Show further it's at the origin later, then it's necessary that it started at the same point. Okay, that again seems reasonable. And then that's it. Okay, so this, although it looks horrendous and I can't actually see the solution straight away, this feels like I can just fight through this problem quite comfortably. So that'll be one of my first, hopefully one of my first 4. Okay, this is actually 2 questions on this page. I thought there was a lot of writing. So 7, we've got 2 functions. Notice the difference is we have f all positives and g oscillating signs. Show by considering a geometric series that f, yep, well I can say that this is less than the GP with a common ratio of that, so that's reasonable. By comparing consecutive terms so that g is that, or you can probably put some bound on each of these plus minus pairs, so that's reasonable, that's reasonable. So for positive integer n, that these things are both integer. Okay, now this is starting, yeah, if I look right to the end, this is giving me some feelings of the proof that e, or in this case e squared, is irrational, are both integers. Okay, presumably we're just going to pick a really, really big n and it will work. Things will cancel nicely. That seems reasonable. Not as confident, but sit down and do it and it should be okay. Show that if, so this is assume that's exactly the condition that e squared is rational, just rearranged in some silly way, then that is an integer for all. So this is going to be my contradiction. That's reasonable. That's reasonable. This is on the maybe the lower end of definitely tackle, but nothing in there surprises me too much as what should be able to do given the time. Question 8. This one's a bit more scary. Straight away we're talking about curves. We're talking about curves, 2 linear curves. Both of these sections are linear, and we're showing they represent a pair straight, so they basically create a cross in some way on the Cartesian plane. Show further that represents, so that's going to be part I is implying that I should factorize this, and then the condition on, well, I can factorize it in the nice way. If in the remainder, C1 is the equation and C2 is the simpler equation. So that one's just a quadratic. That one is some kind of nonsense. It's almost x is y plus s squared plus something. So probably writing it like that is going to be super helpful. Explain why the coordinates of any point which lies on both satisfies that equation. Yeah, I'm just going to sub one into the other. Given that such an S intersects at 4 points, show that choosing k equals 1 gives an equation. Now k is... Where is k in the question? Explain why the coordinates... Oh, k is some unknown... Interesting. Okay, maybe this isn't as certain as I thought because they've introduced an extra variable in there. If I keep skimming through, show that if they intersect, then S is a bound, and then show if S is a bound, we intersect. So that's the both directions of that implication. This, I'm going to put quite a heavy question mark to the cross side. This is on the geometry side, which I know I'm fairly weak at. Not certain how it's going to work down here. Maybe I come back and do this as question 6. But I would probably try and avoid this question. Moving into the mechanics section, these. So unless this has something really obvious, these are, for me, an avoid. Skimming through here, we have an origin on a smooth table. Smooth sphere is at rest and the lowest point at the origin. Another sphere with the same mass and radius, so that's important for kind of the centers lining up and not causing weird collisions. Its lowest point has y coordinates, so I've got some kind of surface. I've got a sphere and then another sphere at certain points. B is projected parallel to the x-axis and strikes there. Show that collision B moves with that velocity. Now, of all the mechanics questions, collisions was my strongest, but this has got a lot of trig work. There might be quite a bit of unpleasant visualization trying to work out here. And we're talking about the lowest point of the sphere, which if you've got two spheres colliding, then they collide not at their lowest point, they collide halfway up. So we've got some weird extra radius worth of distance apart. So that's quite awkward. I'll put this as a definite maybe. And again, if I ran out of pure questions, I've already ticked quite a few pure questions. I may come back to it. Question 10, cube of uniform density is placed. Another one is placed on top of it. So I've got two, and the one on top is smaller. The centre of mass of the upper cube is vertically above the lower cube. So we've got some centre of masses. Both are uniform density, so we do have them perfectly lining up. They are rough connections. There's a lot of information here, and I'm already thinking this is a maybe. Horizontal is exerted perpendicular to the vertical face of the obstacle is halfway between the two vertical edges of the face. So we've got some kind of force here at a distance h from the lower end, so I've got some distance. There's going to be some potential rotation here. There's going to be sliding here. We have some force. This is the classic, which I found while practicing these questions, of a question which looks fine. It looks like we're just doing forces, but something about the question can go wrong. And something about the question can go awkward, and it just becomes too awkward, too heavy, and just takes too long. So I'll put that as a maybe. For me, I like the stats questions quite a bit. So let's see if these are ones which fit well with me. We have a couple of summations which we're allowed to use. We're trying to show some condition. That is probably just using the definitions of the NCR. Hence, show that, well, that might use what's already above. It might be able to, yeah, it looks like this summation just fits in here within the limits change. So I think that's fine. A fair coin is tossed. This is going to lead to a summation. Now, within the normal stats, expectations isn't something you deal with an awful lot. In the further stats, it does. I quite like dealing with expectations. I'm quite comfortable dealing with that. This one's a part 3 feels a bit out of place, but we could probably just write out the condition and maybe differentiate it to show it's a decreasing function. And then finally, choose a value, we pay n, it's tossed a number of times, you win equal to the larger the number of heads and the number of tails. Okay, that's another expectation. I'm expecting that to match some of the summations which we've already dealt with to come into play with this a little bit. Not going to go through all the details, but I'm pretty sure that is quite a comfortable question when I come to it. Finally, question 12. A point is chosen at random in the square. Mixing probability and geometry, already a bit wary. So the probability the point lies in any region is equal to the area. So we're uniformly firing a dart at a square board. So we're equally likely to hit any area. R is given the distance from the center. Show the cumulative distribution function. Something I haven't looked at in a very, very long time, but that's basically asking you the probability that your score is less than or equal to R, i.e. you live inside of a circle of radius R, and yeah, here's the condition. This upper bound is exactly, oh no, this is awkward. So this is when the circle is purely inside the square. This condition here is when the circle has got too large and I've got some square outside the circle and some circle outside the square. Okay, show the expectation. That's that's just an integration formula. That's quite reasonable. And then finally evaluate that. If I look to that integral above, is that an integral I'm happy with? This section down here is giving probably Sine or Cosh inverse vibes, which kind of matches with why we've got a ln in the denominator. So I'm likely to use some kind of substitution of R equals Sine U or Cosh U. Deal with the formulas later. This, other than the geometry here, which is quite awkward, but if I really think about breaking up that circle up, I'm looking for this area here, so I need to lose the area there from the square, then maybe this question is doable. I'll put this as a question mark for now, but it's on a topic which I like, even though it's combined in with some geometry which I don't. Okay, so that is what I'd suggest you do at the beginning of every step paper. Maybe not straight away as you're starting to work out which questions fit well with your skill set, but once you start moving into doing the full 3-hour papers, a good 5 to 10 minutes, I know we spent a lot longer than that in the video itself, picking which questions, picking which topics sit well with you, picking which don't sit well with you to avoid, and again hoping that you've got maybe 4 questions that you've ticked. I've got 1, 2, 3, 4, 5. So I actually ticked 6 questions, which I think I'm quite comfortable with. Maybe I just got lucky with the topics on this paper. Maybe I haven't analysed deep enough to work out whether they are comfortable or not. But those are the questions which then I'd tackle. And before actually committing to any of these, even though I've ticked them, I would reread them and check that I'm not going to commit time to something that I'm not comfortable in completing. So if you do watch the rest of this playlist, you'll see each of these questions tackled, whether I thought I should tackle them in an exam situation or not. There will be video walkthroughs of them in the following. Until then, good luck for all your practice that you're doing yourself.